So remember from the last lecture, I told you guys that descriptive statistics is just a set of mathematical procedures for organizing, summarizing, and simplifying data. And often we have many variables that are measured for many participants, and that amount of data is pretty unmanageable just to look at it and glean any information from it. Just a whole bunch of numbers that don't make a whole lot of sense. So this lecture will cover the simplest way to describe data, which is by using frequency distributions. And with frequency distributions, you simply count the number of each score or response, or participants within each category, to determine the proportion of participants that have each different score or response or in each category. So today I'm going to tell you guys about the steps for creating a full frequency distribution table. The full frequency distribution table provides a lot of useful information, but going forward, we are going to be using a more simplified version of the frequency distribution table to do calculations for the rest of the semester. Then I'm going to talk about interpreting and calculating values from a frequency distribution table. So using that simplified, not the full, but the simplified frequency distribution table to figure out how to add up all the scores or figure out how many different data points or people there are in our data set. And that type of information will be really useful for all the calculations that we're going to be doing for the rest of the semester. Then I'll move on to constructing frequency distribution graphs, so just creating a picture with the frequency distribution table, and then how to look at those frequency distribution graphs and determine the shape of the distributions. And part of the reason that we talk about the different shapes is because, first of all, it gives you description of the data, but also throughout the semester, different types of statistical analyses will be more or less appropriate for data based on the shape of the distribution. So here are the steps for creating a full frequency distribution table for a single variable. So this full frequency distribution table not only includes all the possible range of scores in your data set, how many times those scores appear in your data set, but it also gives you the proportion of what proportion of the data set have this specific score, then turns that into a percent, and then uses that percent to calculate percentiles. So I'll go through each of these steps with an example here in a second. But first, you will create a table with these 5 columns. These are the labels along the top row of the column. Then you want to identify the highest and the lowest values in your data set. And you'll create a row beneath the X column, or that first column that you created, for each possible score response option, and from highest to lowest, top to bottom. Now, it's important to note that you may have some gaps in your data set. Like you may have some scores that are 5s and 4s and 2s and 1s with no 3s, but you still want to include that 3 in your frequency distribution table. Now, for nominal variables, the label rows are just words. They're not numbers, and you can put them in any order. But again, if you have data that is numeric in nature, then you will want to go from highest to lowest, top to bottom in your frequency distribution table. Now the third step, you just want to indicate the number of responses for each X in the adjacent rows. So next to each X row, you're going to have an F column, and you're just going to count how many times that particular value, that particular X value, appears in your data set. F just stands for frequency. Then step 4, you'll find the proportion for each X value by just taking the frequency and dividing it by N. N is just how many total scores are in the data set. Then you'll want to find the percentage of participants with each value in your data set, and you just simply take the P that you found, the proportion, and you multiply it by 100 for each X value in your data set. Then you'll want to find the percentile rank, or the cumulative percent, or in other words, what percentage of participants have a score that's less than or equal to X, each X value. And that's really important for where you want to see how you fall relative to the other people in your data set. So for instance, if you take an IQ test and you're told that you're in the 90th percentile, well, it's really exciting because that means that you did better than or equal to 90% of test takers. Or in other words, only 10% of test takers had a higher IQ score than you. So the frequency distribution table that you use these steps to create is going to provide a clearer picture of the trends in your data versus just having mass amounts of disorganized data in Excel or in some other data analysis program. So you can answer questions like, do scores tend to be high, low, or in the middle? Are scores clustered together or spread out among possible scores? In other words, what's the degree of variability in my data set? You can also figure out how single scores compare to the entire distribution of scores. For instance, which percentile are you for the IQ test? Or let's say that you're measuring performance review scores of employees at Winco. You could see what percentile somebody who has a performance review score of 6 on a scale of 1 to 10. So let's go ahead and do an example that demonstrates all those different steps that I mentioned before. So let's say that you have some raw data that looks like this. It's pretty disorganized. There's a clear pattern here. You can see that there's a whole lot of zeros in this data set, but overall, it's not really clear what the data looks like. And let's say that this data represents the number of missed sticks for blood draws among nurses at a hospital in the past week. So let's just go ahead and deconstruct this quickly. So here's the raw data, disorganized, and then this first column here, this would be like your X column. So X is just kind of a placeholder for whatever variable you're measuring, in this case, missed sticks on blood draws. And what you do is you find the highest score and the lowest score, and then you put those scores in order from top to bottom. So if you look here, you'll see the highest score is a 4 and the lowest score clearly a 0. So some nurses had 4 missed sticks, and that was the most number of missed sticks among all the nurses. And then some nurses had 0, and that was the lowest number of missed sticks among all the nurses. And just to recap, this would be a ratio discrete variable. It's ratio because the measurement tells you the direction and magnitude of the differences. So someone who had 3 missed sticks has more missed sticks than somebody with 2, and it's 1 more. And it's discrete because there's a true 0 point. You can't have negative missed sticks. 0 is as good as it gets. So step 1, you place your range of variables in order from highest to lowest, top to bottom. Now the second step in this process is your frequency column. So you want to count how many times each one of these numbers appears in your data set. And if you go up here, you'll find that there's, if we look for 4, there's 1, 2, 3 4s in this data set, and that's why 3 is there under the F column. So all the full range of numbers appear in your data set, and then how many times each one of those appears. Now the P column, this is the proportion column, and this is where you take that F divided by N for each X value. And N in this case, I'll show you this next slide, is 51. So you get N by adding up all the frequencies. So how many scores are in this data set? And we'll come back to this slide in a minute. So 51, 3 plus 2 plus 7 plus 2 plus 37. There's 51 total scores. You could also get that number by counting. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to 51 numbers here. Add these together. That just tells you how many scores there are. Okay, it's a lot easier to add these than to count all these up. So 3 out of 51 nurses had 4 missed sticks. So the proportion of nurses with 4 missed sticks is 0.059. The next one, 2 out of all 51 nurses had 3 missed sticks. 2 divided by 51 gives you a proportion of 0.039. Now people like to interpret numbers and interpret proportions in terms of percentages. It's easier for us to understand. We talk about percentages all the time, whereas proportions isn't as easy to understand. So we can turn these into percentages. So 0.059 times 100 gives you 5.9%, which may be easier to describe than proportion of 0.059. So for each one of these, you just multiply this by 100 to get the percentages. So far, this is pretty straightforward. But then when you get to the percentile, or the cumulative percent, it becomes a little bit more complicated, but I have the full process spelled out for you here. So you start with the lowest score. Because remember, the cumulative percent, or the percentile, tells you what percentage of scores are equal to or less than this specific or particular score. Well, if 0 is the lowest score in the data set, well, then there are no scores lower than it. So 72.5% of scores are equal to or less than, even though there's no less than, 0. So then to get to the next percentile, you'll add the percentile for the score below it to the percentage of scores with that value. So to find the percentile for one missed stick, you add 72.5 to 3.9, and you get 76.4. So in other words, 76.4% of all the nurses in this data set have as many or fewer missed sticks than a nurse with one missed stick. So just moving up, you keep doing this process. So you'll take 76.4, add it to the percentage for 2 missed sticks, and you get 90.1%. Then you take 90.1, add it to 3.9, and you get the 94th percentile. So in other words, a nurse in this data set that has 3 missed sticks is at the 94th percentile, meaning that 94% of this sample had just as many or fewer missed sticks than she did. Or in other words, only 6% of the sample had more missed sticks than she did, or he. And then up here, this gets you up to the 99.9th percentile. Because pretty much, within rounding error, 100% of all the scores in this data set are at or lower than 4. So here is the same exact table that I just went through, only I have summations here, just adding all the scores together. This little sigma just means to sum. So again, 3 plus 2 plus 7 plus 2 plus 37 gives you 51. There's a total of 51 nurses in this data set. Then if you add all the p-values, or the proportions, or the probabilities is another way to say it. So you could say that there's a proportion of 0.059 nurses in this data set with 4 missed sticks. Another way you could say it is that the probability of randomly selecting a nurse with 4 missed sticks from this sample is 0.059, or 5.9%. We're going to be talking about P a lot this semester. Just keep in mind P means proportion or probability. Those two terms are pretty much synonymous with each other. Okay, enough of that tangent. So the sums are here for a reason. You can check your work to see if you're doing things correctly by seeing if all of these proportions added together come very, very, very close to 1. There's rounding error here. We didn't carry out to the full extent of the number. We rounded to the thousandths place. So you may have something that's not exactly 1, but it should be very close to 1 when you add these together. That tells you that you're doing something correctly. Conversely, when you add your percentages together, you should have something really, really close to 100%, because this represents all of the scores in the data set. Now, when you get to here and you add these together at the top for the percentile for the highest score, they should match the sum that you got here when you added these together, because again, it's cumulative. You're adding them up as you go up. Okay. So remember I said that you can answer questions with the frequency distribution table. So how many people were in the sample? 51. You get that by adding up all the frequencies. How many people had more than 2 missed sticks? Well, you can say, all right, more than 2 missed sticks. Well, that would be people with 3 and 4. So 3 plus 2 gives me 5 people that had more than 2 missed sticks. This is a lot easier to determine with this table than it would be if I asked you the same question and just gave you this raw data. Another one, what percentile is someone with 3 missed sticks? Well, 3, they're at the 94th percentile, which tells you that 94% of the sample had less than or equal to 3 missed sticks. What percentage of people had 2 or fewer missed sticks? Well, this tells you, this basically describes percentile. What percentage of people had 2 or fewer? So you could go straight to 90.1. Remember, the percentile tells you how many people had that score or lower, 2 or fewer. So 90.1% had 2 or fewer missed sticks. You can also find that by adding up the frequencies for everybody that had 2 or fewer missed sticks. So 7 plus 2 plus 37, that gives you 46. And then taking that total and dividing it by the total sample size. So 46 out of 51 people in this sample had 2 or fewer missed sticks. You divide that and you get 90.1%. So that's just an example of creating a frequency distribution table and figuring out some characteristics of data based on that frequency distribution table. Now, it's also important to be able to calculate values using a frequency distribution table. So if you look, we've simplified this. The only thing that came from before, I'm keeping this X and F columns. What's my variable? What's the full range of scores in my data set for that variable? And how many times did those scores appear? So when you're doing calculations, I would recommend that you just keep these two variables or these two columns, and you don't worry so much about these here. And you'll understand why here in a second when I go through and show you how you can use the frequency distribution table to do calculations. So if I ask you, what is the sum of all scores? Or in other words, the sum of X. So you can't get the sum of X by just saying 4 plus 3 plus 2 plus 1 plus 0. Remember, this doesn't tell you how many times those values appeared in the data set. It just tells you the range of values. The way to get the sum of X, the sum of all the scores, or how many missed sticks were there in total in this sample, you have to take the frequencies into account. So you have to multiply X times F to then figure out the frequencies for each different group, the total frequency or the total sum of X. So you'll take 4 times 3. 3 nurses had 4 missed sticks, 12 in total. 2 nurses had 3 missed sticks, 3 times 2, 6 total missed sticks. 7 nurses had 2 missed sticks. 7 times 2 gives you 14 total missed sticks. 2 times 1, 2 nurses had 1, 2, 37 times 0, 0. So when you add all these together, then that gives you the true sum of X, the true total missed sticks in the sample. Now keep in mind, if you had access to the raw data, you could also just say 2 plus 0 plus 0 plus 0 plus 4 plus 0 plus 0 plus 0 plus 2. Just add all those together and you're going to get 34. But sometimes when you have large data set, it's a lot simpler to just do this method. 4 times 3, okay. 3 times 2, okay. 2 times 7, there it is. All the way across and then add to get that sum of X. And sometimes you won't have access to the raw data. You'll just have this and you'll need to do some calculations. So it's important that you understand that. So again, you take X times F all the way across, add that together. See, there's where Fx comes into play, F times X. And then you can add those together to see how many total missed sticks or whatever variable that you're looking at are in the data set. Now this is important because you're going to be calculating means or averages throughout the semester. And to figure out the average or the mean, you have to find the sum of X and divide it by the total number in the data set. So what is the sum of all the scores divided by how many scores I actually have in my data set? So 34 divided by 51 gives you an average of 0.667 missed sticks in this sample. And eventually, we're going to get to calculating the sum of squares, which helps us calculate measures of variability. And part of that is asking you to calculate sum of X squared. And remember the order of operations. You have to take the exponent before you sum. So we have an operation where we need to take the exponent. We need to square each x value. So that creates this new column where we square each x value. 4 times 4 is 16. 3 times 3 is 9. 2 times 2 is 4. 1 times 1 is 1. And 0 times 0 is 0. But just like before, where we needed to find the sum of x, you have to take the frequencies into account. You can't just add these up and say, oh, well, the sum of all the squared scores is 16 plus 9 plus 4 plus 1. Again, you have to take the frequencies into account. So you'll create a new column where you take each frequency multiplied by each squared score across the board. So 3 times 16, 2 times 9, 7 times 4, all the way down. And then you'll add those values together to get the sum of squared scores. Now you could also, if you had access to the raw data, square each one of these and add them together. So 4 plus 0 plus 0 plus 0 plus 16 all the way across, and you would get 96. So one of the main reasons to put data into a frequency distribution table is to use that frequency distribution table to create a frequency distribution graph. This makes it easy to detect the shape of the data, which we'll talk about here in a little bit. So before I go into details about how to construct these graphs, I just want to point out some details or some different aspects of the graphs. So the x-axis, that would be the horizontal axis at the bottom of the graph. You want to label the x-axis with whatever your variable is. In this case, I'm looking at all the majors that are in this specific Psych class, or the Psych 210 class. So as you can see here, most of you guys are nursing students. But the x-axis represents whatever variable that you're measuring. So you'll label what is the variable, and then you'll have all the different values of that variable represented on the x-axis. And although this example doesn't lend itself to this because this is a nominal variable, if you're using a variable that's quantitative in nature, you'll want to start from the lowest to the highest, from left to right. So as you'll see here in a little bit, when we look at the missed sticks, you'll start with the lowest number and then go to the highest value from left to right. And then the y-axis is the vertical line that's on the left side of the graph. So you'll want to label the y-axis as frequency, and then you'll want to represent the full range of frequencies that are present for the values in your data set, from lowest to highest, bottom to top. It's okay to count by 2s or 5s or 10s if there's a large range of frequencies. So as you can see here, the frequencies range anywhere from 1 to 20. So just to keep everything simple, I counted by 2s here on my y-axis. So whenever you're creating these, you want to make sure that not only you label what the variable is and each different level of that variable or each different value of that variable, but you also want to label this frequency and then report the range of frequencies here in whatever way makes sense. Now, what you want to do next is you want to plot the data for each x value by locating each x value on the x-axis and then drawing a bar from that x value to the height of the appropriate frequency. So if you look here, you'll see, okay, pre-nursing students, there's 20 of them. Here's pre-nursing, and I draw a bar that goes up to 20 here. Nursing students, there's only 1. Nursing, a bar that goes up to 1 on this frequency axis. Now, there's 3 different types of graphs, and the type of graph that you use depends on the scale of measurement for your data. So I mentioned earlier that major is a nominal variable. It's not numeric in nature. There's no meaningful order that you can place these in. So when you have nominal or ordinal data, you need to use a bar graph. And a bar graph looks like this. The height of the bars represent the frequency for each different category, and the bars do not touch. So for a nominal scale, this space in between each bar just emphasizes that the scale consists of separate and distinct categories. Now, if we were using an ordinal scale, so let's say we were measuring the class standing of people that are in Psych 210, so freshman, sophomore, junior, senior, well, the bars don't touch there because you really can't assume that each category is the same size, and they are separate categories. So again, bar graph, nominal or ordinal data, and the bars do not touch. There's spaces in between. Now, if you have interval or ratio data, then you'll want to use a histogram. And a histogram is a lot like a bar graph, except the bars touch. You still want to label what is the variable that's being measured down here on the x-axis and all of the full range of values. And you want to label this frequency on the y-axis and then the full range of frequencies in whatever counting method that makes sense. I did 2's here as well. And you still have a correspondence between the frequency distribution table and the graph. So 0 missed sticks, whoa, 37. A lot of people in this data set had 37 missed sticks. Some good nurses here. And then 1 missed stick corresponds to a height of 2, a frequency of 2, and so on and so forth. So again, when you have interval or ratio data, you use a histogram. The bars touch. You can also use a polygon, which is coming up next. But let's focus on the histogram for now. So interval or ratio data can be continuous or discrete. In this case, we have, again, ratio, discrete data, but you could also have continuous data, so maybe like the number of hours worked in a week. Well, that would be ratio continuous data. So for continuous data, you have upper and lower real limits, which I talked about in the last lecture. And these upper and lower real limits capture the true intervals between response options. So the bars touching for each x value, halfway above and halfway below each x value, represent these real limits. Now, that would make sense if we had continuous interval or ratio data. But in some cases, like this, you have a measure that's on an interval or ratio scale of measurement that's not continuous. So you want to still use a histogram to indicate that each category is the same size. So although these bars touching don't represent some interval that's in between the numbers of missed sticks, but it does represent the fact that these are each 1 apart. So 2 is 1 higher than 1, 3 is 1 higher than 2. Each of these categories have the same width. Now, the next one that I want to show you is a polygon. And it's really useful for detecting shape, which I'll talk about here in a little bit. And it's just like the histogram, only you'd use lines instead of bars. So an easy way to do this is to put a dot at the height that represents the frequency for each different category. So dot here, dot here, dot here, dot here, and then just connect them with a line. And that's a polygon. That's also a correct graph to use, or an appropriate graph to use for interval and ratio data. So if you have a variable that's on a nominal or ordinal scale, you always want to use a bar graph. If you have a variable that's on an interval or ratio scale, then a histogram or a polygon are both appropriate displays of that data. So one major characteristic of distributions of data is shape, and that's what's revealed by these frequency distribution graphs. So the shape of a frequency distribution graph is just created by tracing a line across the tops of the bars or by using a polygon. So if you wanted to draw a line across the tops of these bars, you would get something that looks like this anyway. So one of the major important things about shape is that it helps us determine what kinds of measures are appropriate for our data. So in the next lecture, when I talk about measures of central tendency, we'll go into detail about how different measures of central tendency are more or less appropriate for different shapes of data in your distribution. Now, shape is categorized in terms of modality and symmetry. Symmetry is just basically getting at if you draw a vertical line at the midpoint of your x-axis, do both halves match? In other words, if you folded your graph in half, would the two sides be a mirror image of each other? So in symmetrical distributions, the halves do look like a mirror image of each other. And then in skewed distributions, the scores tend to pile up on one side or the other. When you fold the graph in half, it's not going to be a mirror image of each other. So if you have scores that pile up on the high end, then you have a negative skew, low end, positive skew. And I'll show you pictures of these different distributions here in a second. Now, modality is the second way to describe shape. In other words, how many peaks or frequently occurring values are there in the distribution? So you can have a unimodal distribution, which just means that there's only one value that occurs most frequently. Or you can have a bi or a multimodal distribution where you have two or more values in your data set which occur most frequently. So let's go ahead and look at some pictures of shapes of distributions. So this first one on the left is the normal curve. This is really what we're going to focus on for the most part of the semester. So the normal curve. So basically, most scores pile up around the average, and then we have some extremes on either end of the distribution. So still the variable, the different values for the variable are represented on the x-axis, the frequency is here. So again, most scores are in the middle of the distribution, and then there's extremes or outliers on either end. This distribution is rectangular, and the rectangular distribution basically just means that all variables have the same number of scores. So there's no difference in frequency across all the different values for whatever variable that you're looking at. Now, both of these shapes are unimodal and symmetrical. So if I folded this along this line here, folded it in half, both sides would be a mirror image of each other. Same thing happens here. They're symmetrical. And they're unimodal. There's only one mode here. Here, there's really no mode. So this is more of a unimodal shape here. Now, this is a bimodal distribution. And this is multimodal, just meaning there's more than two modes. So you can identify the modes by the peaks in the data set, the high frequency points in the data set. This is also symmetrical, assuming I did this correctly. It's not perfect, but pretty much if you fold this in half right here, you would see a mirror image. Now this one is not symmetrical really unless you fold it right here. If I was a better illustrator, then these would be more perfect. But assuming I did this correctly, fold it here, you would have a mirror image on either side. Now these are non-symmetrical unimodal shapes. So we have a clear peak in both of these, a high frequency part of the distribution. There's a clear value for whatever variable is being measured that occurs most frequently, or that's the most common. Here is a negative skew, where the tail end of the distribution, the skew or the outliers, are in the low end. Remember, scores are presented from highest to lowest, highest here, or lowest to highest, left to right. So most people have a high score, and then some outliers out here have a low score. And this is a positive skew, where most people are falling at the low end of the distribution, and then we have some outliers that are in this tail end of the distribution, in the high end of the distribution, in the skew, you could call it. Now, one way that I used to remember the difference between the positive and the negative skew shape is if I flip this over, it would look like a P. So that's just kind of a way that you can easily identify the positive skew versus the negative skew. So as we go forward this semester, it's going to be important for you to know how to take raw data and put it into a frequency distribution table, how to use a frequency distribution table to do calculations based on the values in your data set, how to identify nominal, ordinal, interval, or ratio scales of measurement to figure out what the most appropriate type of display or frequency distribution graph you can use for your data, and how to use the frequency distribution table to then create that frequency distribution graph. And it's going to be important for you to identify what is the shape of the data so that you can then decide what type of analysis is most appropriate.